When dozens of microservices communicate synchronously over HTTP, a single traffic spike can take down the entire system. One service slows down, the service waiting on it times out, and that bottleneck cascades, causing a chain reaction of failures across the network grid. To untangle these dependencies, we place a message queue in the middle. It acts as an asynchronous buffer. Producers drop data into the queue and immediately move on, allowing consumers to process that data at their own pace. Neither side needs to know the other exists. For this specific design, we have a strict set of constraints. We need to handle kilobyte-sized messages, guarantee high throughput, enforce strict ordering, and maintain persistent data retention. That last requirement sets us apart. Traditional queues hold messages in memory, just long enough for them to be consumed and then delete them. If we want long-term retention and the ability to reconsume historical messages, we have to use an append-only log structure. Achieving massive scale and historical replayability forces us to abandon volatile in-memory architectures. We have to build a durable, disk-based event streaming platform. In a traditional point-to-point model, a message is consumed by exactly one consumer, and then it is gone. To allow multiple services to read the exact same data, like a billing service and an analytics service, we use a publish-subscribe model. To organize this data, we use a high-level logical container called a topic. Producers write to a topic, and consumers subscribe to it. Hosting a massive topic on a single server creates an immediate bottleneck. The system slices that topic into partitions, distributed across separate broker nodes. By splitting data, we enable horizontal scaling. Multiple nodes process the same topic in parallel. On the reading side, we organize instances into consumer groups. To maintain order, we enforce a strict rule. A single partition connects to exactly one consumer per group. By locking one partition to one consumer, we guarantee a strictly ordered sequence of events inside that partition. Strict global ordering across an entire system is impossible at scale. We explicitly trade global ordering for strict partition-level ordering to achieve massive horizontal scale. When storing these messages, traditional relational and NoSQL databases fail. The constant, heavy read and write loads quickly overwhelm a standard database. Instead, we use a write-ahead log. It is a plain append-only file. As you can see with the spinning platters of a physical hard drive, seeking out random sectors takes time. By relying exclusively on sequential disk I/O, we avoid random seek times completely. This sequential writing allows the system to exploit aggressive operating system page caching, hitting throughput speeds of hundreds of megabytes per second. Since a log file cannot grow infinitely, it breaks data into segments. Messages append to an active segment. Once full, it slides over to become inactive and read-only, and a new active file takes its place, making it easy to truncate old data. Every message shares a strict structure: a key for routing, the value payload, the topic and partition, a sequential offset, a timestamp, and a CRC check. Maintaining this exact message contract across the producer, broker, and consumer enables zero-copy routing. The broker never needs to unpack or mutate the message. It moves raw bytes directly to disk, eliminating expensive CPU overhead and making physical disk I/O the system's only true limitation. When a producer sends a message, it uses a hashing algorithm on the message key to dynamically route that specific message to its assigned partition. Sending these messages one by one wastes resources. Producers group messages into batches, amortizing the high cost of network round trips. If a broker pushes data, a slow consumer gets overwhelmed. Instead, we use a poll model. The consumer fetches a batch of data, processes it, and commits an offset marker. Because logs are persistent, different groups can independently rewind and replay historical data. Shifting flow control trades minimum latency for system-wide stability. When a massive traffic spike hits, consumers simply catch up when they can. Distributed clusters are inherently unstable. Consumers crash, broker nodes die, and traffic patterns force you to dynamically scale. If a consumer drops offline, its coordinator detects a lost heartbeat. It triggers a consumer group rebalance, electing a leader to safely remap the orphan partition to a surviving node. To manage this complexity, brokers rely on external coordination services like Zookeeper. These key value stores track topology, manage leader elections, and hold metadata, keeping brokers highly performant. To prevent data loss, each partition is replicated. Producers write to a leader node, while follower replicas pull data to stay synchronized. These up-to-date followers form the in-sync replica set. If a follower falls behind, the system evicts it, preventing it from stalling write availability. Isolating state coordination from raw message routing prevents a single point of failure. It allows the data plane to scale entirely independently of the control plane. When a consumer fetches a message, it must commit its offset. Committing before processing yields at most once delivery. It has low latency, but if the consumer crashes, data is permanently skipped. In at least once delivery, the consumer processes data entirely before committing the offset. If it crashes before acknowledging, it pulls duplicate data upon restart. Exactly once delivery is possible, but requires distributed transactions that severely impact system throughput. System reliability is not a binary state. You explicitly tune acknowledgements and commit timings, trading latency for durability based on your exact business requirements. Traditional message queues optimize for transient, single-use latency. Event streaming architectures optimize for durable, replayable throughput. Achieving infinite scale requires sacrificing global ordering. We maintain strict sequential integrity only at the partition level. We balance physical hardware limitations with logical design. Sequential disk I/O lets us squeeze hundreds of megabytes per second out of standard rotational drives. Designing a distributed message queue is about mastering tunable constraints. There are no perfect systems, only perfectly calibrated trade-offs.